I will now make some remarks about how to do this lab. Some things to think about, problems that can occur, or opportunities for improving the speed. So, first, what do you need to do for a push? Well, clearly you must have a node with excess preflow greater than 0, and to do the push it must have a height that is higher than the neighbor that it wants to push to. When you do a push, do you need a reply? And what should the reply consist of? Can you do many pushes before waiting for the replies? If you can, then your program will be faster. Whether that is required or not has not been decided yet, but it will be in the PDF for the lab as part of the requirements. But you should want to do that. If you think of it, I mean a similar scenario, say you have a chat application and an actor wants to send a message to multiple persons or actors, then clearly you would want to send many messages at the same time and not waiting for a reply from each actor, which would make it very slow. The same thing happens at the machine level. When some event has happened in the machine at a cache block and several parts of the machine needs to know about it, then the machine will send many messages at a time and not wait for a reply from each before sending the next. So in general we should always try to identify when we can increase the parallelism in the program. Okay, when we do a push, we clearly need to traverse the adjacency list of a node. And it's I call this function discharge, and it's quite common to do so. And what it does is it is responsible for doing either one or more push or a relabel of a node. One way to iterate through the list is to use a plain while loop, and that may be more useful than a shorter one-liner, because you may find that you need to wait for a message before something happens. And okay, I will not explain any more details about this, but just to make you aware of that it can be useful to start like this, and probably is. But do as you want, of course. Okay, that's it. Well, I should say also that this approach of a while loop, it is relevant also in the case when you send multiple push messages before waiting for a reply. That scenario probably will happen. Okay, so what to do in the lab? The guaranteed best approach to make the lab in a smooth way is to start drawing the simplest possible graph on a piece of paper and decide which messages need to be sent and received in order to find the maximum flow of that input. Don't look at the source code. And when that works, try to make the input, I mean not try, but make the input bigger and see that your algorithm still works. And when you are convinced that it does, you can look at the source code. Okay, so what you will get is incomplete program, which does the following. And then you need to write code for somehow going through the adjacency list and do push or relabel. And you also need to tell the controller that a node has become active or become inactive. Don't let the controller ask the nodes whether they are still active. Let the nodes tell the controller instead when the status of active or non-active changes. Okay? And also, any solution which relies on a timeout is not passing the lab. Okay, the main program has a timeout, but that's not counted here. But for instance, a wrong solution, which is not a solution, would be that the controller sets a timer that if no node has done anything for the last X number of seconds, then probably it's finished. That's not okay. It must calculate whether it's, it must determine by itself whether the algorithm is finished and not relying on time. Okay, now some problems that can occur. The first is related to message arrival order. Recall, two messages from one actor to another, they always arrive in the order that they were sent. But if two different actors send a message to a third actor, then we don't know in which order they arrive. So this can break the program. Suppose there is only one remaining active node. Let's say it's U, and it pushes everything it has to a neighbor V. So now U is no longer active, and it will tell the controller that it's no longer active. But V is going to become active and will tell the controller that it has become active when it has. Or you do these messages in some completely different way. But just say that it's done like this. Then what can happen is that the message from U reaches the controller before the message from V. So when the controller sees that U is no longer active, then it can terminate the program, and that was not intended, since V would soon become active. So how can this be solved? Well, that's an interesting thing to think about, but I will not tell you. Okay, another thing is decision making. When there is only one actor involved in a decision, then it's easy. But in the preflow push algorithm, two nodes are involved in determining whether a push can be performed or not. So let's see what we can do. So let's assume that U asks its neighbor V for its height, and V replies with the height, And U is excited to see that the height of U is higher than the height of V, so it sends flow to V. But before it does, or before it arrives, V has already done a relabel. And that means that flow should not have been sent to V. This is just an example of a problem when multiple, in this case only two though, actors are involved in decision making. So how can you avoid this problem of not violating any algorithm invariant? Something to think about. Okay, another thing is how to make debugging relatively easy. The problem with the debugging parallel programs is that the execution is not deterministic. So if it works almost always but has a bug, then it's a little bit of a problem. So you want to have no bugs. And well, that's quite obvious, but what you should do if the program doesn't work is to take the smallest possible input and make printouts and see that the program behaves as you expect. Okay, you can probably find it useful to compare the outputs with the sequential preflow push C program that is in lab 0, which is not a lab, it's just, well, it's called that. It doesn't matter. Okay, with lots of printouts, there is a Unix command called grep. Grep stands for global regular expression print. It was a command to another command, and then it was so useful, so this acronym was created for this program. What it does is to look for a string on each line, and it prints each line with that string. So if you run your program and save the output in a file and have enabled the debugging output, then you can search, for instance, what is happening with node 1 using this string, since at 1 is the printout for anything that the node 1 does. Okay, so that's a hint.